For my project, I investigated how to use group theory to determine if two knots are the same. Knot theory was actually first used in chemistry in the late 1800s in the study of atoms. Before we knew modern atomic models, scientists believed that atoms were made of knots, and lighter elements consisted of simpler knots, while heavier atoms were more complicated knots. Intuitively, a knot is exactly what it sounds like, a string that makes a closed loop in three-dimensional space. More rigorously, it's the embedding of the circle S1 in R3. Here, we see the knot diagram for what is called the trefoil knot. At each crossing, a small gap is used to indicate which arc passes over the other. The most basic way to categorize knots is by the smallest number of crossings in any of its diagram, called its crossing number. Ideally, this would be easy to calculate, but the same knot can have two different diagrams with different numbers of crossings. For example, the unknot without any crossings, and shown here on the left, can be twisted so that it has one crossing, but it's still considered the unknot. Similarly, any knot with two crossings is also equivalent to the unknot in a way that we will investigate later. It also turns out that the trefoil knot on the right is the only knot with three crossings. We can consider knots with more and more crossings, where there is only one knot with four crossings, but two knots with five crossings. At this point, knots are denoted by the number of crossings in a subscript, and the number of knots for a given crossing number grows extremely quickly after this. The three most important questions that this presentation aims to answer is determining some sort of operation that can be applied to knots, creating a definition for what it means for two knots to be equivalent, and finding some sort of notion to show two knots are equivalent. One of the most natural operations that could be applied to knots is joining them together by removing a small arc from each knot and pairing together the loose ends, making a bigger knot with more crossings. This operation has an identity, namely the unknot, and turns out to be associative, but it unfortunately does not have an inverse for every knot, so this does not form a group. But just like with finite abelian groups, any knot with a finite number of crossings can be decomposed into prime knots. The next question was to figure out what it means for two knots to be the same, like an isomorphism for groups. Intuitively, it should be that you can smoothly transform one into the other without breaking the loop or passing it through itself. Mathematically, this is defined by a function that transforms R3 such that F0 is the identity, the image of knot A under F1 is knot B, and Fs is a homeomorphism for all S in the interval from 0 to 1. Now, it's not important to know what a homeomorphism is. It simply means that Fs behaves nicely. In this case, it means that F is a bijective map between spaces that preserves certain properties of the space, which is similar to an isomorphism. We call this function an ambient isotopy and say that knots are ambient isotopic if it exists. The last question is to answer how to determine if two knots are equivalent. The most direct way is finding an ambient isotopy as was described on the previous slide, but this is very difficult to do. What's often easier is finding invariants for knots, in which two knots are different if the invariant isn't the same for both of them. For example, the crossing number mentioned earlier is an invariant, but although it's easier to calculate than some other things, it's not very powerful. Another invariant turns out to be coloring the arcs, such that at any crossing, either one color or three colors are used, but again, this is difficult to determine. The last invariant, which will be discussed more in depth, involves investigating the enclosing space. To do this, we must first cover some basic topology. Topology as a whole is a study of sets, and a part of this is deciding if two spaces are the same, like we're trying to do for knots. This is where the joke comes from about how a coffee cup and donut are both the same to a topologist because they're both a torus. And the Gordon-Luke theorem for knots says that if the complement of a knot are the same topologically, the knots are isotopic. And so we can investigate the complement of a space R3 minus a knot instead of the knot itself. And to do this, we must first introduce the concept of a path. If we have 2 points in R2, like shown here, although there are many paths you can take from one to the other, they ultimately aren't that different. In other words, if I said the path from P to Q, there wouldn't be much confusion because ultimately it doesn't make too much of a difference which path is taken. Now, instead imagine R2 minus a single point, denoted by this gray circle. Now these two paths from P to Q are actually different. If I said the path from P to Q, it would be unclear if I meant going to the right or left of the hole, in which case it might make a difference. Rigorously, two paths are equivalent and called path homotopic if there exists the special function f that smoothly deforms a path alpha into a path beta. Interestingly enough, this function has a lot in common with the definition of an ambient isotopy defined above. But most importantly, homotopic paths form equivalence classes under this operation. The next step is to make an operation on paths like we tried to do with knots. If we want to merge paths together, then it would only work if the end of one path was the start of the next. In this case, then we can travel the first path in half the time domain, and the second path in the other half of the time domain. Now, this operation technically isn't associative because of how it allocates time for each path along the domain, but if we instead consider the operation on equivalence classes on paths instead of individual paths, it is associative. So ideally, we want to be able to find some structure in this, but as it stands, not every pair of paths can be operated together like this. To solve this, we consider only paths that start and end at the same point, which are called a loop. If we consider the operation applied to loops, then it turns out this forms a group. It has an identity, which is the path that doesn't go anywhere, and the inverse of a path is walking the path backwards. And the notation used is pi sub 1 of the space and the base point. As an example, the fundamental group of R2 with any base point is the trivial group with only the identity, because any loop can be reeled into the identity loop. On the other hand, the fundamental group of R2 minus the origin with any base point is Z, the integers, because a loop is classified by the number of times it winds around the origin. Finally, the fundamental group of the unit circle S1 is also Z because of the same winding number argument. As the last example suggests, if a space is well behaved, in this case it means its path connected, its fundamental group is independent of the base point, which is a good property to have. To see this, given two different base points in a space, we can start at one base point, take a path alpha to the other, walk around a loop, and take alpha back to the start, which defines a homomorphism between the fundamental groups at each base point. Since this homomorphism can be applied both ways, and with a little hand waving, we can see that these two groups are isomorphic. Now finally, we can relate this back to knots. We can consider the complement of the knot in R3, and if two knots are isotopic, then their spaces are equivalent, and so the associated fundamental groups are isomorphic. Another useful fact is that the converse is true, but only for prime knots. That is, if two knots have the same fundamental group, then they're equivalent knots only if they are prime. Unfortunately, this is not true for composite knots, and the square knot and granny knot are one such example of composite knots that are different with the same fundamental group. It also turns out that the group associated with knots usually aren't the kinds of groups that we're used to, like the set of integers or the set of units. So for an example, we can calculate the group associated with the unknot by noting that a loop path is categorized by the number of times it winds around the knot. So just like before, the group is Z, and also written as the group generated by X, where X is a loop. And the reason for this will make sense soon. Another useful fact is that since the unknot is prime, it is the only knot whose associated group is Z. For a slightly more complicated example, if we have the trefoil knot, then we can loop a path around any of its three arcs. If we call each such loop X, Y, and Z, we could say that the group is generated by X, Y, and Z. But this isn't quite right. If we zoom in on one of the crossings, like as shown in this diagram, it turns out that going under Z then X, which gives the path ZX, is the same as going under the bottom left X and then Y, which means that ZX equals XY. If we apply this logic to the other crossings, the fundamental group is the group generated by X, Y, and Z, such that ZX equals YX and ZX equals YZ. But with a little bit of algebra, we can simplify this a little more so that we finally conclude that it's the group generated by X and Y, such that XYX equals YXY. So on the slide are some of the sources I used to make this presentation if you're interested in learning more about anything mentioned. I hope you enjoyed.